Howdy! It's just your friendly neighborhood physics teacher. Today we're going to talk about how the big four physics kinematic equations come from. We talked about the kinematic equations in class, but I'm going to show you where these equations actually come from, so maybe you can understand a little bit more on how these equations interact. So first we're going to go over I'm going to write down the four equations so you know what I'm talking about. The first equation is just your V final equals your V initial plus A times delta T. Now remember, V is for velocity, A is for acceleration, T is for time. This is your equation 1. Kinematics equation 1. No fancy name, just that. This equation comes from the slope of your velocity versus time graph. So if we have a velocity versus time graph, what is your slope? Yes, it's acceleration. Yay! Acceleration. So if we do our slope equation, slope equals our change in y over change in x. If you look what our y is velocity, and our x is time. So therefore, our slope equals our change velocity over change in time. Now, we've already said our slope's acceleration, so acceleration equals our change velocity over change in time. Now, the change one time, that triangle is a delta. That triangle is a delta. That means change it. So pretty much mathematically, what that's saying is you do your final minus your initial. So we can break that down and put that into our equation. So acceleration equals V final minus V initial divided by your change in time. You can break down your time, but most of these equations, or for all these equations, we do not. We keep the time as change in time because, like I said, 98.5% of the time, you're just going to give one number for time. You don't have to break it up between final minus initial. Now there's your slope equation. To get this equation to look like our top equation, all we have to do is manipulate. So our goal is to get our V of f by itself, right? That's basically our goal. We're trying to get that by itself. So we need to, let's see here. So our delta t needs to come over here. It's being divided, so the opposite of dividing is multiplying. And what you do to one side, you have to do the other. So those end up canceling out. You get V final minus V initial equals delta t times A. And now, again, we want this V final by itself, so we need to get our V initial on the other side. It's being subtracted. The opposite of subtracting is adding. So we add it to both sides. What you do to one side, you got to do the other. So we get our V final equals delta t times A plus VI. Now that doesn't quite match up to our top equation. It's a little off, but there's a way that we can kind of move it around, because this equal sign means this side just equals that side. So you can flip what's on either side. So we have delta t times A plus VI. So at least got the VF on the same side. But again, as long as you're adding, it doesn't matter which one you add first. So you can do your VI plus delta t times A. And again, with the multiplying, since it doesn't matter which direction you multiply, you can flip those two. So with just a little manipulation, you can get our first equation. Yay! So this equation comes from the slope of our velocity versus time graph. Now, for our second equation is, like I said, this one's not used a lot. Our second equation is delta x equals 1/2 v final plus v initial times delta t. Where this one comes from is the area under the curve with a velocity versus time graph. So you remember we have a velocity versus time graph, and we have like a shape that's area under the curve. We can break this down. That would be one shape, and this would be another shape. One of those two shapes. So the green one is a rectangle. So the area of a rectangle is just your base times height. Area of a triangle is 1/2 base times height, because a triangle is half of a rectangle. So while you're doing that, we can just add up. We want to find, the total displacement. We have to add up our areas. So we add up area of the rectangle, and we add up the area of the triangle. That's basically the gist of it. Because we're just trying to find displacement. After you manipulate all that fun stuff, you end up getting to our second equation. And I'll work that through. So if we do our delta x equals our base times height plus 1/2 base times height. Now, what is our base? What is our height? Because we don't see base times height in this equation. In this case, our base would be time, and our height would end up being velocity. So we have delta x equals, our base is time, and we're going to do delta t because times our velocity plus 1/2 base. It's going to do change velocity. Okay, 1/2 again, change velocity times your change in time. And here again, we're just stepping it through. We're just manipulating. So we leave our delta t alone, and we end up, again, most of the time we have a velocity in front of our change in time. So we have we end up having a change velocity times delta t plus 1/2, and we can break our final minus our initial delta t. We can spread that out a little bit more. Change velocity, change in time. So if we manipulate, we end up getting plus 1/2 final delta t minus 1/2 vi delta t. We can break this one up too. Probably should have done that, same thing. So again, if we end up getting your final minus your initial delta t, and then plus all of that, you can distribute, so you get delta x equals your v final times t minus v initial times t, plus, again, all of that. Now, you can start seeing, we can start having different things manipulate. So, you end up, because things end up adding and subtracting, you end up getting 1/2 the final delta t plus 1/2 the initial delta t, and then you can pull out just how we did before. So you have your final plus your initial times your delta t, and you get to our equation. Again, drawn out method, but as long as you realize that this equation comes from your area under the curve, you are set. So our third equation. Our third equation is one of the most used equations we have in our big four. So basically, where this equation comes from, it comes from the first. It comes from the. Excuse me. It comes from the first equation you've dealt with, and it comes from the second equation. Put a 2 by that. That needs to be 2. Deals with our first equation and our second equation, kind of manipulating. So we start out with our first equation, which is v final equals v initial plus a delta t. And remember what we do to one side, we want to do the other. So if we end up adding v initial to both sides, you end up getting just v initial plus your v final equals, well, we have 2 of those now, 2 initial plus a delta t. This right here, you can put a parenthesis around, and then again, what you do to one side, you do the other. So we can go ahead and multiply 1/2 delta t to both sides. Running out of room on this side. And so we end up getting 1/2 v initial plus v final delta t. So that's our second equation. Equals, yep, I have to bring this over, so 1/2, 2, those cancel, and you have your delta t, so if your v naught delta t, and then again you have plus 1/2 acceleration delta t squared, because it's going to both of those. This right here from our just equals, change in x, and you get our third equation. I forgot to box that one. So you get our third equation. So again, that one's a little bit stretched. Pretty sure how they thought, if we add initial to both sides, then we get multiplied 1/2 t squared, or t delta t, yeah, that is our most used equation. So last but not least, we have our fourth equation. So if you remember, our fourth equation is our final squared equals initial squared plus 2a delta x. Now, this one comes from the slope equation multiplied, pretty much it's your first equation multiplied by your second equation. So we have our, so if we have our acceleration times our delta x equals, so our acceleration, remember from our slope equation, is our v final minus v initial delta t. We're multiplying by the x, we're going to use our second equation, which is our lovely 1/2 v2 plus v final, v initial delta t. Again, it's just manipulating to get things to look a little bit prettier. So you have a is delta x, your delta times end up canceling, one on the bottom, one on top, and you can end up distributing your, because you can end up having distributing your v finals and v initials, but we can, before we do that, we want to get rid of this 1/2, so we're going to multiply 2 by both sides. It's 1/2, so we multiply that by 2, then we can go ahead and bring this out. We have finals by v initial, and we have v final plus v initial. So again, you do some manipulation, you end up getting v final squared plus v initial times v final minus v initial times v final minus your v initial squared. So those end up canceling because you're adding, ones that add, ones that subtract, getting up to a delta x equals minus v initial. And at this point in time, it's just manipulating to get it to look like our earlier equation. So we get v final squared equals your 2a delta x plus v initial squared. Again, just like our first time, to get it to look like the equation that I've presented it to you, you can flip it, equals 2a delta x plus initial. Again, adding or subtracting, you can manipulate it either or, and you get to our fourth equation. So that's just how you derive the equations. This is not going to be testable. I just know some people like to know where the equations come from. So just to recap, your fourth equation comes from your first and second equations. This is basically your first equation. That's your second equation. Your third equation comes from your, like I said, remember this one's the fun one, comes from your first equation and manipulating to get to your second equation. Your second equation comes from area under the curve. So it comes from area under the curve. Yeah. But remember, we put curve in quotation because it's really not a curve. And your first is the slope. So hopefully that helps understand where the equations come from a little bit better. You're not going to be tested on how to derive the equations. That's just there to help for the ones that need to know. Hopefully you have a wonderful day. Bye.